I see, like I can see which, like if you go to the YouTube, you'll see which of the lectures is most viewed. You get some kind of statistics.
I
So
think sliding mode
sliding,
one
yeah.
probably was the one I watched the most.
I watched the 4 lectures twice, or maybe 3 times.
Yeah, I watched them.
So,
I don't think I watched sliding
Actually, I
mode
couldn't do all
2
of them.
maybe like.
so
I only did the first.
topic is called adaptive. Backstepping is like a tool again. I said right. The topic is more of a this adaptive control. But because you are mixing things, you can. So this problem will kind of give you a motivation. So it's, let's say we have x1 dot equals to x2 plus theta 1 psi of x1, okay, and x2 dot equals to u. So that's a problem in hand we have, right? This awesome problem that we have, right? So now the question, the thing that is, we don't know anything about this parameter. There is an unknown parameter there. We only know that this is a constant parameter. That's at least it's unknown but constant. At least that part is there. Okay.
No boundaries for it.
Huh?
No boundaries.
No boundaries, no upper bound, no low. Only I don't know anything about it. Only thing I know is it's constant. So that's another like for sliding mode you needed some information to cancel things out. Right? So here we don't have anything except that this is constant. Like for example, gains of your autopilots. Let's say you bought a DJI Mavic Air and you are controlling, and it uses PID, right, to control the attitude or something, and it uses some gains. So you don't know what those gains are, and you want to, right? So those kind of problems. Length of the rod in a pendulum. It's unknown, totally unknown. Let's say, but you don't know anything. It's constant though. L dot is 0, theta dot is 0. Okay, so the only thing is it's constant. Okay, so let's begin the fun. I'll explain you what is the adaptive part when we reach there, but what will be the first step? You want to first is like it's like backstepping problem, right? I want to first goal is pick up this, right? This equation where I want x1 to go to 0, right? X1 to go to 0. So let's say v1 equals to half x1 squared. So that's first Lyapunov candidate function. v1 dot equals to x1 dot, which is x1 dot is this, right? x2 plus theta 1 phi of x1. Okay. Now what should be my x2 such that I can make this thing negative definite, right? There are two problems here, right? If I start applying cancellation, I cannot apply the cancellation thing because I don't know theta. So now what we can do is, let's say instead of theta, I have an estimate theta 1 hat of it. Okay. For now, theta 1 hat is the estimate that we will run in parallel to this, right? If it was known, then I could have cancelled like x2 equals to minus theta 1 phi x1 and then minus k x1 would have been added. So if this was known, right, if this is known, then what will be my control? What will be my x2, choice of x2, right? So x2 desired then will be something like this, right? x2 desired will be minus theta 1 phi of x1 minus k x1. That will solve the problem, right? That will give me v1 dot equals to minus k1 x1 squared, right? So but that's not the case. The case is that this is not, so all I can hope for is theta 1 hat, and then tried to make theta 1 go to theta, right? So that error goes to 0. But for now, let's say this is the best I can do. Like I have x2 desired is this, right? Questions? Which is equal to, you can say, phi 1 x1 theta 1 hat. It's a function of x1 and theta 1 hat, right? So having said that, let's start adding things to this equation, right? Let's modify it. So x1 dot equals to x2 plus theta 1 phi of x1. So we can add and subtract this part, right? Just add and subtract, so like adding a 0, so it will be minus theta 1 hat phi of x1 minus k1 x1 plus theta 1 hat phi of x1 plus k1 x1, right? Okay, so when I do that, what happens? What happens is, what I can do is, see, this and this cancels out, isn't it? Or no?
Well, you just added that in there, so
No, sorry, yeah.
you probably need to grab that theta 1 hat.
Phi one this. Let's not cancel it, I just added. So let's first do the math here. X2 equals to, so what I can do is, see, I want to define a theta bar term, which is theta 1 minus theta 1 hat. That's an error, right? So if that error goes to 0, we kind of will be good. So we'll see how that error can go to 0, but plus Vx1 minus Vx1, okay. So now if you see, that will give me this, right? So it will give me theta 1 bar, which is this, right? Phi of x1 minus k1 x1 plus theta 1 bar phi of x1 I'm thinking minus plus k1 x1, right? So yep. Just confused with the one term here. Z2. Okay, yeah, we have to define a Z2 also, right? So this is phi of x1, right? This is equal to minus of phi of x1, right? Where is my x2 desired? This is equal to minus of x2 desired, right? This term is minus of this. So basically this is x2 minus x2 desired, right? This is x minus x2 desired, remember, right? So we can take that. So this is, and then plus theta 1 bar phi of x1 minus k1 x1, right? So this we can define at z. We also want x2 to go to x2 desired, so that's z. So we can rewrite our equation as z plus theta 1 bar phi of x1 minus k1 x1, right? Now that's x1 dot. Now we can plug this in and see what v1 dot will look like. So v1 dot will be x1 dot, right? So x1 dot will be, so z x1 plus theta 1 bar phi x1 minus k1 x1 squared. Okay, so that's the V1 dot. That's, we wanted this to be this, but right now things are not zero. Neither Z is zero, neither theta bar dot is zero. Theta bar is zero. So that these two terms keep hanging there. We will make our controller such that that will make these two terms go to zero then. Okay, so they keep hanging there. So that's my V1 dot. So let's go down the line. So now comes the interesting part here. Let me. So let's first take care of this term here, and this is where the adaptation part will come. So what if I choose my V2 to be V1, okay, the previous one, which is half 1x square plus 1 over 2 gamma. Gamma is just some constant, and I want to make this theta bar squared. Okay, so I don't know theta bar, but I want to at least get rid of this thing. Okay, theta bar. It will be, so let's see what it will be. V2 dot then. V2 dot will be V1 dot plus 1 over 2, and gamma is just, it's a constant. It will be used as an adaptation gain actually. Gamma is adaptation gain, how fast you want your parameter to adapt to that unknown parameter. So that's gamma. So it will be 1 over gamma theta V1 dot theta bar into theta bar dot, right? That's the differentiation of this, right? So now let's plug in the values of V1 dot. V1 dot is zx1. So from here, right? From here it is z2x1 plus theta 1 bar vx1 into x1 minus k1 x2 square, x1 squared, sorry. It should be x1 squared, and 1 over gamma theta bar dot. See, this is not known to me, but again, let me just highlight this. Neither theta and theta bar is known to you, because to find an error you want the actual term. So you need to, because see, what is theta bar? Is theta hat minus theta? What was that? How do you define? It was theta 1 minus theta hat. So this is also not known to me, right? So now let's do some more math, and see, we have common terms here. We have theta 1 here, and we have theta, let's keep theta 1 constant, and z x1 is there. So just if I take this theta 1 bar common, it will be z x1 plus minus just x1 squared, and then I will do this theta 1 bar outside from this and this. So theta 1 bar outside, then it becomes phi of x1, and it becomes minus. Oh, what happened? Did I mess up with a sign somewhere? I messed up a sign somewhere, so I'm not sure. So that's theta 1. If I take theta 1 bar outside from here, yes, you know what happened here? So see, when I differentiate this, what happens? What is the differentiation of theta bar dot? theta bar dot equals to theta 1 is constant, so that's 0, minus theta 1 hat dot. So instead of doing theta bar dot, I can write it theta hat dot, theta 1 hat dot.
Minus.
So it becomes minus here because there is a difference between hat, this bar, and hat. Okay, so this is hat, so it becomes negative. So now I have 1 over gamma theta bar into theta 1 hat. Okay, see, even though I don't know theta bar, so theta bar goes outside, sorry, this is common, so 1 over gamma minus theta 1. So this is not known to me, but if I make this 0, then doesn't matter what this theta 1 bar is, right? Right? So what I do is, this is the magic trick here. Let's choose, because I can choose how because theta 1 hat is my parameter, right? We choose it. So I can also choose how fast it changes. Theta 1 hat is the rate of change of that unknown parameter. Your guess. So I can choose this rate at least, if nothing else. Rate is known, I'm not breaking any laws there, right? So is equals to, and this is known, x1 phi of x1, there is no problem in knowing. So that is equal to gamma phi x1 x1. What happens then if I choose theta 1 hat dot to be that? That's your parameter, right? You have added one more state to the system and you're deciding what is the rate of change of that state. And then this disappears. It disappears, right? Now we have equation which is equal to v2 dot equals to minus v2 dot equals to z x1 minus k1 x1 squared. That's all, right? So that is taken care of. Now we have this here. That's not an issue. Okay, so now let's go. So that is called adaptation law, if I have to write it. Adaptation law. That's what, and you can choose how fast. This gamma is the term where you can choose how it will adapt to the system. Now what is remaining? You can take another one more layup now and say v3 equals to v2 plus half z squared, right? To get rid of z now. So v3 dot will be v2 dot, which is z x1 minus k1 x1 squared, and z dot, and z dot is what? Z into u, basically. Z dot, no, z dot is not u, sorry. So it will be plus z dot. What is z dot? Z is x2 minus x2 desired, remember? And our x2 desired was x2, so the x2 dot is u and x2 dot desired, basically. And x2 desired was, I think, was minus theta 1 phi of x1 and minus k1 x1. I think that was x2 desired, right? Oh, sorry, hat, sorry. There was a hat, right? We didn't know actual one. So that's how we chose the x2 desired. So now what will be x2 desired dot? X2 desired dot will be x2 desired dot will be, or you can call it basically or this is also phi of x1 theta 1, right? Just to shorthand notation for this. So this will be, so x2 dot will be phi of x1 into x1 dot, and then phi of, so this will, if it is phi of x1 theta 1, x2 dot is first with respect to del phi with respect to x1 into x1 dot, right? I'm trying to get a time derivative of this, which is a function of x1 and theta 1, right? So this plus del phi by del theta 1 into theta, theta 1 hat, it's theta 1 hat into theta 1 dot, right? So we can plug it in here. So u minus del phi by del x 1, x1 dot is x2 plus theta 1 phi of x. I don't know, I think I took the harder example to start with. Somehow I think there was an example where it would have been easier, and so that's x1 dot, and del phi over del theta hat is theta hat 1, and this is already known to us. What is this theta 1 hat dot from here, right? So we can plug in that. What is that? Gamma phi, was it phi of x1 into x1, right? Yeah. So that. Okay. See, I'm doing this because I exactly don't know what phi of x is. That's why phi of x. So that's why we are keeping it in general terms here. So that's, having said that, so now we can multiply things. U minus del phi over del x1 into x2 minus del phi by del x1 into theta 1. We took a wrong example, guys, to start with. And because I wanted to show you first just the adaptation part, here we are doing double adaptation, so I don't think we should. Let me finish it and then we'll come back, and then we have del phi over theta 1 hat I think I took a wrong example. Let me adaptive. Yeah, sorry. So the example what I want to initially start with was like having this equals to u. So there was just first order equation, which is x1 dot equals to u plus. That's how what I wanted to start with, but kind of ended up in this because what the logic is still the same, but here for the same parameter I have to estimate this parameter 2 times to cancel things out, but it will be more clear if we do the first part. So basically instead of x2 desired, it is just u. So let's say my equation here, right, is x1 dot equals to u plus theta 1 phi x1, right? So basically this was u here. Okay, u equals to minus theta 1 phi x1 minus k1 x1, right? So we can rewrite this thing just, and then this will not appear. Let's just do a slide right here. So what we could have done here, right, if you see, oops, sorry.
Please, thanks.
Okay. So, oh, time is over. So, we'll continue this in the next class. That's not a problem. Start with this example. So there are two approaches. What I wanted to hint here was you can make this V2 dot go negative definitely in one shot or two shots. So one shot is this approach. If you do in one shot, then you will need two estimates of the same parameter. If you go in one shot, like I also had half z square also here, right, in the same V2, then you can go in one shot and have one estimate of the parameter. So it's how you want to approach the problem, but it's different use with both the ideas to show things negatively. So you go here and then go, you'll see that life become easy. But here I could have just done in one shot, z dot, and come up with one theta head dot, and rather than two theta head dots at two different steps. It's the game of the adaptation rate. So that gamma, you can choose now how fast you want things to convert to. Questions? Do you like it? Are you amazed? Because the next thing, after we do one or two examples like this, simulate it, show it to you. We'll do a UAV 2D tracking problem using the same approach. And there, if you see two things, right? In a 2D UAV simulation, let's say x dot equals to v cos psi, right? Y dot equals to v sin psi. That's a very simple 2D kinematics. And now let's say we have v dot equals to kv. Autopilot is there, which is v commanded minus v. So your input is v commanded. So you give it, and it generates an acceleration. And then similarly, your psi dot is k psi commanded minus psi, right? So if you see, input is v commanded and psi commanded, but we don't know what kv and k psi is. How will you come up with v commanded? What should be v commanded and psi commanded, such that it tracks a trajectory? So that will be the next problem that we will do. And I think take home exam is just convert it to 3D. Just telling you from now on. It's the same problem now, but you have v cos psi, cos theta, sin theta, and then you have six states, and you add one more state, your life becomes hell here. So even though you will have perfect solution in front of you for 2D, it will be hard to.
And that's what you're making for the test?
Yeah, that's
Okay.
the test.
All right.
The midterm or the final?
The midterm.
Mm.
Okay, that's the test. So that's. But again, I'm doing it 2D and then giving you a problem, so you cannot complain like until else. You have never seen this before. Teaching class. So the next assignment, I don't know if you saw the posted assignment tomorrow. Some will be doing AUV, some will be doing transfer functions.
Oh, you're talking about for the TA class? I mean, for the model simulation class on TA.
Again, so it is x1 dot equals to u plus u plus theta, some phi of x1, right? And so again, here only first order equation, because I want to show adaptation first before we even move to the backstepping part here, right? So now, so there is one equation, so v1 equals to half x1 squared, right? So v1 dot equals to same thing, it's x1 into u plus theta phi x1, right? The problem is I don't know theta, right? So if you knew theta, then u equals to, it would have been u equals to minus theta hat phi of x1, because I don't know u, I just take an estimate, minus kx1, right? Simple, which will give me, if theta equals to theta hat equals to theta, then v1 dot will be, v1 dot will be minus kx1 squared, right? Not an issue. But it's not the case, so but that's my controller, right? So what you can do is, you can say x1 dot equals to just plug it in here. So when you plug this in here, it is theta minus theta hat, right? Because that's the case. Phi of x1 and minus k1 x1. Okay, so that's my x1. So, and this is theta bar, right? So x1 hat equals to theta bar phi of x1 minus k1 x1. And v1 dot becomes, if I plug in, then v1 dot then becomes x1, because x1 dot, right? x1 dot, which is equal to theta x1 theta bar phi of x1 minus k1 x1 squared, right? Now we can go and we want to get rid of this term, so we say v2 equals to v1 plus half gamma theta bar squared, right? And then v2 dot equals to v1 dot, which is x1 theta bar phi of x1 x1 minus k1 x1 squared, and this becomes minus 1 over gamma theta bar into theta hat dot, right? So now game will be over here. Now if you say, I can bring this, so I can take out theta bar, then it becomes x1 phi of x1 minus 1 over gamma theta hat dot, right? Now you can choose theta hat dot, like it's doing the same example up to that step. Theta 1 hat dot is now gamma x1 phi of x1. So if you choose this theta hat dot, then this disappears, right? v2 basically minus k1 x1 squared, right? So this disappears, so that means the v2 dot is then minus k1 x1 squared. Okay, so now let's going back to the controller. Now what do we need in the controller? Where is my controller? Yeah, here. So we have shown that if we choose this controller u and theta hat dot this, then we are good. This is negative definite, right? And this is called adaptation law. So I can rewrite my u again. U equals to minus theta hat phi of x1 minus k of x1, right? Now where does this come from? By solving this equation. See, we can, it's a theta hat dot, right? So theta, if you integrate it, see, it's not a function of actual theta 1 hat. Anything is not a function other than the controller. That's the magic here. So you start theta 1 hat with some initial condition, any initial condition, and then just put it in S function, right? An additional state in S function. What will this give me? When the S function is solving, it will give you theta hat, right? If theta hat is available to you, then that means the control is available to us. But the magical thing is, you will see when I do the simulation that, see this, you are thinking that theta bar will go to 0. Theta bar never goes to 0. And there is no role here. It doesn't. I have never, at no point I have come across a point which says that theta bar should go to 0. All I am saying is my theta hat dot should be this. If theta hat means the rate of change of theta hat is what we want, then doesn't matter what actual theta hat is. So that even though controller is using actual theta hat to cancel things out, but eventually you will see that even though it doesn't, because everything is this rate, because this rate, the rate that I choose makes my v1 dot negative definite. So v1 dot is never was a function of, after that cancellation, of theta 1, actual theta 1 bar, which we never know. So even though this here in the controller you are using theta hat, which never converges to actual value, it still works. That's the magic here. Like I don't know, the importance is of the adaptation rate, because rate is what we are using to cancel out the bad terms, not the actual theta 1 hat. So you see the rate here is what I chose, because theta bar is coming outside, right, as a common term. So if this goes to 0, it doesn't matter what theta bar is. So let's check the simulation of this. So that's why I wanted to give you a simple example, so that the next step will make sense. So in next step, the difficult example that I was doing was, what happens is, you have to apply two different rates of the same parameter to cancel things out. Same parameter, but two theta 1 hat dot and theta 2 hat dot. They are the approximation of the same parameter, but you are choosing two different rates. One varies at a different rate, another varies at a different rate to cancel things out to make that even dot negative. So even though, so that was the complicacy there, but we will get that. But do you imagine it working even theta hat is not the actual value? That was the initial game, right? Like if we are thinking that theta hat will converge to theta, right? And that will make my u working, but I'm telling you that theta hat, at no point, all we care about is theta hat dot. Then whatever comes out of it, the change in theta hat dot is what is important, not the actual. That's the important point I want to make. So let's go and check if we got that simulation somewhere. So the only thing in simulation is we have to choose some phi of x1, that in the first equation. But let's see if I have it. So the book is very nicely, like I'm exactly following the notes, like exactly comes from. So if you see this example here, right, u equals to, they are using different names, like instead of kx it is using cx. So don't get confused by this, but other than that, it's not a problem. So let's go and check if we have something here. MATLAB inverted. MATLAB inverted pendulum, UUV sliding mode. No. Adaptive is not there. Homework solutions. No. So we can create one if needed, but let's say box sync, important from box. Adaptive control. Yeah. Adaptive control. Parameter. So again, I have a. So if now we are simulating this system, right? What do we need? So now what I do here is, when you simulate this, right? So am I using a y theta and y dot? Is this the same example? No. Adaptive, 2D, 3D. Maybe we should just implement it, because I don't think I have an example here, because this uses 3 states, right? So 3 states means controller. So equals to theta minus p. So u seems to be same, but where is my s function? System dynamics. So system dynamics is, what's the number number of states, continuous states to p dot x 0. Yeah. So what we are using here is x1 dot equals to u plus, if you remember, there was theta 1, right? Theta 1 was there, and then phi x1 was there, right? So instead of phi x1, we are using x squared, right? So x1 squared basically. So that variable is just this variable, right? And then so in this case, so this is the case we are implementing. So now you see you add one more state to it. You add theta 1 hat equals to gamma x1 squared into x1, right? So it becomes x1 cube, I believe. X2 dot is gamma into x, yeah, so it becomes x1 cube. So that's the adaptation. So you add one more state to it, right? So your S function, your initial conditions will be x1, whatever the x1, and then theta 1 for theta 1. And then u basically is parameters y, theta. Yeah, so it's same thing, two variables, right? So no, not a problem. Plot data. Okay. Let's see the controller here. So if you see controller, it's just simple, same thing, right? U equals to theta hat into x2 square. So u, see, u is pretty simple. Choosing u was not a problem, right? U was the one which, assuming that if my theta 1 is equal to theta 1 hat, you choose your u. So your u was what? U was minus theta 1 phi of x1, which is x1 squared, minus k x1, right? That was your u. Now instead of this was theta 1 hat. So that is your u. To compute u, you need both theta 1 hat and x1, right? So this S function outputs you x1 and theta 1. That goes to this controller. And so all you do is add an additional state. See, but we did not make any assumption on the theta 1 parameter, right? What is the big value, small value, nothing. So so if you see in simulation, in parameter, if you go, I'm choosing theta 1, actual theta 1. So your system knows this theta 1, right? So that is 11. The actual theta 1 is 11. That's what you use in S function to simulate the behavior. But as a controller, I don't know it, right? So that's good. So let's run it, and then we'll show you. So what I want to show here is, see, this is where did I start? I started at 11.2. I mean, so that's a very good guess because I am simulating things. But you can choose different value. For now, let's see the results with this. But we can choose whatever value you give me for the theta 1 hat 0. That's your S function needs an initial condition to solve theta 1 hat. So whatever, I'm saying it is 11.2. Actual is 11.
Okay, so for this problem, you only were given x1 dot.
Yeah,
So-
that's
so
for the
that's just-
simulation. That's for because that's a plant, right? In here, I have to make plant also, right? That's always deal.
Right.
S function is my plant.
So, but in that same S function, you're also adding the estimated term?
Yes.
Okay.
But you don't need to. Your controller, you can have a separate S function. Or
That's what I was wondering, if you
Yeah.
needed two S functions or if you put it in the
Yeah,
same one.
if you have if you're doing real time, you will have to solve this ODE separately, basically, right? Here, because I can group it into the same thing. But in real life, it's a plant, and you actually
Right,
solve
right,
this
right.
equation to feed it here. Okay, so that's the thing. Yes, good question. So yes,
So,
here just for
but I
my
might start the habit of doing two
do
different.
two S functions.
Okay, all right.
Yeah, you can definitely. So that the output of the second S function will be u.
Okay. Got it.
Exactly.
Okay.
Right? Yeah, so that's perfectly.
Okay.
Yeah, you should use two S functions.
Okay.
to make it a more looking like more of no
Realistic,
cheating
yeah.
problem. That okay. So if we go and see plot data, right? So plot data, we'll see all these plots. So this is my U. That's my controller. So you see U goes to 0. And this is my theta, actual theta. So you see actual is 11. I started 11.2. It converged at 11.9-ish. Not the exact value. Exact value is 11.
So it got worse.
Huh?
It got worse.
It doesn't. So as I said, it doesn't matter what it converges. The rate at which it is varying will always be same, right? So we'll see when we choose different values. But if you see x, oh man, see, it goes to 0. It's beautiful. Okay, now let's go and do changes. For example, instead of 11.2, let's make it 0, which is like, this is totally like 11 points off from initial value. Let's run it, and then let's run this simulation again for 30 seconds. So rate, it will be totally different value where it converges. So, but your U uses that value, but somehow it happens that because U is also time varying, right? So that change in theta 1 hat because of the time varying nature cancels out the bad terms, not the actual theta 1 hat. Okay, so if we do plot data again, you will see. So that's my U, right? Of course, U changes, but theta hat converges to something like 22.5, which is totally different. I think where it starts and so then x again goes to 0, right? There will be impact on how the trajectories, like how when it goes up, overshoot and all that jazz, but when we said it goes to 0, it goes to 0. So that's the rate of change of that parameter which matters, not the exact parameter what you estimate. So rate is like, see, I start at some theta 1, 0, right? The rate is means when you integrate it, you'll add something to theta 1, 0. Any questions on this?
Yeah, can you explain me again, like why do we need two S functions?
See, in real life you will have a plan like this. So this is your f of x u, right? You give it u, it gives you x with some initial condition. So in real life this is the case, you are already getting an x. So you want to design a controller, right? So where you take in x and you need theta hat here, theta 1 hat. Where do you get that theta 1 hat from? So you have to solve that theta 1 hat dot equation, right? So you can have an S function here. This can be an S function where you're solving for you're solving for theta 1 hat dot, which gives me theta 1 hat, which then you use it to compute u, and which then gives you here. Here I'm assuming that I'm solving both equations together because I don't want to put two S functions. Right? So that's the point. But again, the point is the adaptation rate. The rate is responsible for making that Lyapunov V1 dot negative definite, not the actual theta 1 bar. So that's kind of very hard to digest sometimes, that because I'm using this here, right? And this value is sometimes 22.5 and sometimes it is 11.8. How can of course the control, but at the end x1 goes to 0, x1 goes to 0. Doesn't matter. The rate is important. And the even magical, the next question that we were doing, you will, in the same controller you will have like theta 2 hat, and these are the parameters, say, estimates of the same parameter theta. So even two values, same parameters, two different adaptation rates going in two different ways, but still it works. So that's pretty amazing from what my perspective. Nothing was known. We kind of, and all through the math, so guarantee and all. So sometimes it's easier to digest these concepts if math is supporting it, right? If it was, oh, something is happening, like let's say you do, somehow somebody gave you this controller, right? Let's go and implement this controller and see what happens. And you say, hey, it's converging. And they say, oh, why is converging? Like, you change this value or again, as somebody gives you a second controller which looks same, still converging, then you won't be able to figure that out, right? Oh, why is it converging even if I don't exactly know this? But then this adaptation rate mathematical analysis shows you that you have shown that V1 dot is minus less than equal to minus K1x equals to, which is less than 0 all the time, negative definite, boom. So that's the power. If you, I don't know if you realize all we are doing is V1 and V1 dot throughout the course. So now is how we show that, that's the whole different game. How do I show that V1 dot? Now once you have started using controllers, your life will become easier, right? You don't have to get started with complicated Lyapunov candidate functions. Whatever you choose, the simplest one, you work with it and find U. It's just the math that what should be in my U such that whatever I'm doing is shows this V1 dot to be negative. That's the whole idea. So that's it. That's the whole idea. So if we go back to our previous example, second example there. So this, if you go to the